Heat could be transferred from place to place by conduction, convection, and radiation. Today though, we will be focusing on radiation. All objects emit and absorb infrared radiation, even with just a very low amount, but it can still be picked up by a thermal imaging camera. This is a thermal imaging camera for detect the infrared radiation and convert it to the visible light. The hotter an object is, the more radiation it emits. Some of it even become visible light that we can see. Infrared radiation is type of electromagnetic radiation which has a lower frequency than light and involves waves rather than particles. This means then, unlike conduction and convection radiation, can even pass through the vacuum of space. This is why we can still feel heat from the sun even though it is 150 kilometers away from the air. Some surfaces are better than others emitting and absorbing infrared radiation. Dark matter surfaces are good at emitting and absorbing infrared radiation, which is why solar panels are black in order to absorb the maximum amount of heat. For your hot shower, white light shiny surfaces are poor at absorbing and emitting infrared radiation, but they are good reflector, which is how a thermal works. If you want to keep your cup of tea hot all day, you put it in a thermo that is coated inside with a shiny surface to reflect the radiation back to the tea and keep it warm for hours. So far we have looked at conduction and convection, and both of these methods need particle to transfer heat, but heat managed to get us from the sun, and this definitely no particle in space. It's vacuum. So how does the heat from the sun get to us? Well, it travels as radiation. Infrared radiation, infrared or heat radiation to be precise. So let's look more at this process for heat transfer of radiation. We actually find the different colors better at emitting heat than others. Now all hot objects emit heat radiation, and this is physics term of hot. What it essentially means is any object above 0 degrees Kelvin or minus 273 degrees Celsius. That's what a physician means by hot. So anything above that emits heat. However, it will also be absorbing heat radiation, and it's only if it's hotter than surrounding that is actually going to be emitting heat overall. So let's add some boiling water to this cube to make it hotter than the surrounding, and let's see what happens first. Let's look at the shiny silvery side. See the really rubbish emitting radiation. There's hardly any waves coming out of it at all. We then turn to the white shiny side. You see there's only marginally better, still pretty rubbish emitting radiation. The matte white side slightly better but still pretty rubbish. Let's go round to the shiny black side, and we see all of a sudden that is emitting a fair bit of heat now. But now if we turn around again, we see the matte black side. We can see that it's going like crazy, that is emitting a loads of heat radiation, and we can see from this that matte black is the best color at emitting heat radiation. So what color is going to be best at absorbing heat radiation? We have seen that matte black is definitely best emitter. What's going to be the best absorber? So they are really easy experiment for this. We have a nice heat source in this form of fire, and we can stick using just some wax to marbles and a couple of plates. One plate with a shiny surface and the one plate with a matte black surface. So whichever surface absorbs the most heat radiation is going to melt the wax the fastest, and therefore the marble will drop quickest. So which one do you think it will be? Let's look and see what happens. Well, first off, I can notice that this shiny silver surface is reflecting away all of the radiation. The matte black surface seems to be absorbing all that radiation. So I'm going on the arm. There we go, the matte black feel of way in advance of the shiny silver one. The shiny silver one's still pretty stuck on that, and you can see why. It's because the matte black is absorbing all the radiation shiny silver. is reflecting it. So what's the key information for us? So here when heat needs to transfer across a vacuum, the only way it can do it is by radiation. We have also seen that matte black is the best absorber and emitter of radiation. That's why if you want something to heat up really quickly or something to cool down really quickly, we color it black. We also saw that shiny silvery surface with the walls at both absorbing and emitting radiation. And that's why if you want something to stay hot or if you want something to stay cool, we use a shiny silvery surface.
Assalamualaikum. My name is Muhammad Khairul Ikhwan bin Abdul Razak, number matric CD 180112 section 1. I would like to present the radiation heat transfer. So the first slide is the view factor. What is view factor? View factor is a purely geometric quantity and is independent of the surface property and temperature. So it is also called the shape factor, configuration factor, and also angle factor. So in the figure below, the radiation heat exchange between surface depends on the orientations of the surface relative to each other, and this depends on orientation is accounted for by the view factor. So this is the figure. So next is, this is the important equation for this subtopic. Next is, alright, the first one is plane surface, the second one is convex surface, and the third is concave surface. In the figure above, the view factor from a surface to itself is 0 for plane or convex surface and non-zero for concave surface. So next is, the view factor is very useful in radiation analysis because it allows us to express the fractions of radiation leaving a surface that strike another surface in terms of the orientation of these two surfaces relative to each other. So the underlying assumption in this process is that the radiation a surface received from a source is directly proportional to the angle the surface subtends with a view from the source. This would be the case only if the radiation coming off the source is uniform in all directions throughout its surface and the medium between the surface does not absorb, emit or scatter radiations. So the last one is the case when the surface are isothermal and diffuse, emit and reflect the reflector, and the surface are separated by a non-participating medium such as a vacuum or air. So next, view factor expression for some common geometry of finite size 3D. So the first one is a line parallel, the second is coaxial parallel, the third is perpendicular rectangular with a common edge. So this one is for 2D geometry. So the first, this is the first one, parallel plate with midline. The second one is inclined plate. So the third is perpendicular plate. And next is three sides enclosure. So the last one, infinite plane and a row of a cylinder. So view factor relations. Radiation analysis on an enclosure consists of n surface require the evaluations of n2 view factor. So the first one is the reciprocity relations. So this is the relations. So this is the rule. Next is the summation rule. The sum of a view factor from surface I of the enclosure to all surface of the enclosure including to itself must equal unity. So the radiation leaving any surface I or of an enclosure must be intersected completely by the surface of the enclosure. Therefore, the sum of the view factor from the surface I to each other of the surface of the surface enclosure must be also unity. So this is the figure, the example for this summation rule. So this is the equations. So the total number of view factor that need to be evaluated directly for an end surface enclosure. So this is the end surface enclosure equations. So the remain view factor can be determined from equations that are obtained by applying the reciprocity and the summations. So next is the superposition rule. So the view, this is the figure. The view factor from a surface I to a surface J is equal to the sum of the view factor from surface I to the part of surface J. This is the example, and also this one is the important equations for the superposition rule. So next is the symmetry rule. Two surfaces that possess symmetry about a third surface what have identical view factor from the surface. If the surface J and K are symmetry about the surface I, then Fi to J equal to Fi to K, and Fj to I equal to Fk to Fk to I. So this is the example for symmetry rule. So we go to the next is view factor between infinitely long surface, the cross string method. This is another method. So channel and duct that are very long in one direction relative to the other direction can be considered to be a two-dimensional. This geometry can be molded as being infinitely long, and the view factor between their surface can be determined by the simple cross string method. So this is the diagram. This is the figure. So this one is the equations for the cross string method. Okay, the next slide is a black surface. When the surface involved can be approximate as a black body because of the absence reflections, the net rate of radiation heat transfer from surface 1 to surface 2 is. This is the equations for black surface. So this is the example for black surface. Two general black surface maintained at uniform temperature T1 and also T2. The below is the equation, the important equation for the black surface. So next is the continue for the black surface. The net radiation heat transfer from any surface I of an end surface enclosure is. This one is how we want to find the net radiation heat transfer. So the next is diffuse gray surface. Most enclosure encountered in practice involve non-black surface which allow multiple reflection to occur. So radiation analysis of such enclosure become very complicated unless some simplifying assumptions are made. It is common to assume the surface of an enclosure to be opaque, diffuse and grey. Also, each surface of the enclosure is isothermal, and both the incoming and outgoing radiation are uniform over each surface. So next is radiosity. Radiosity J, the total radiation energy leaving a surface per unit time and per unit area in the figure below. This is the example for the radiations. So for a surface I that is grey and opaque, so this is the equations below. The important equation for radiosity. So the radiosity of a black body is equal to its emissive power, since radiations coming from a black body is due to emissions only. So that's all from me. I'm going to pass to my friend. So that's all. Thank you.
Hai, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Syafiq bin Sairul Bahari, and I will explain about net radiation heat transfer to or from a surface. Okay, as we all can see here, we use Q.I to get the surface resistant to radiation. So the formula is radiation leaving entire surface minus radiation incident on entire surface. So we get the AI in bracket Ji minus Gi. Okay, so in this slides, it represents the net radiation heat transfer. We have two surface, that is surface J and surface I. To find the space resistant to radiation, first we need to apply the reciprocity relation to get the Ri. Okay, in an N surface enclosure, the conservation of energy principle requires that the net heat transfer from surface I be equal to the sum of the net heat transfers from surface I to each of the N surfaces of the enclosure. So this is the figure of the network representation of net radiation heat transfer from surface I to the remaining surface of an N surface enclosure. So this is a formula for the heat transfer from surface. Okay, we move to the next slide. Okay, that is here, methods of solving radiation problems. Okay, so this is the long explanation, but we can simplify it by saying that this is a two method that we use, that is direct method and network method. So basically the direct method is suitable when there are a large number of surfaces. Okay, so for the network method is not usually practical for enclosure with more than 3 or 4 surfaces. Okay, we move on to the next slide. That is radiation heat transfer into surface enclosure. Okay, as we can see, this is the schematic of a two surface enclosure and the radiation network associated with it. So this is the formula, and this is important because it is applicable to any two gray, diffuse and opaque surface that form an enclosure. Okay, next we move to the table 13.3. There is radiation heat transfer relations for some familiar two surface arrangement. Okay, there are basically 4 figures that we can see here. First one is small object in a large cavity, and the second one infinitively large parallel plates. Then the third one infinitively long concentric cylinders, and the last one is concentric spheres. So this is the formula from each of the shape. Okay, next we move on to the radiation heat transfer in 3 surface enclosure. Okay, there are lots of formula here, but this one is the simplified from the textbook. So this formula is algebraic sum of the currents. This is the figures. Okay, we move on to the radiation shields and the radiation effects. Okay, a radiation heat transfer between two surfaces can be reduced greatly by inserting a thin, high reflectivity sheet of material between the two surfaces. Such highly reflective thin plates or shells are called radiation shields. So the role of the radiation shield is to reduce the rate of radiation heat transfer by placing additional resistance in the path of radiation heat flow. So the lower the emissivity of the shield, the higher the resistance. Okay, the next one is a radiation heat transfer between two large parallel plates. So this one is formula for no shield. Okay, and next one is radiation heat transfer between two large parallel plates with one shield. Okay, this one is the shields, and the heat transfer from here go through the shields and go to the last walls. Okay, so the formula in the heat transfer. Okay, this one, if the emissivity of all surfaces are equal. Alright, after that we move on to the radiation effects on temperature measurement. As we all can see, this one is a thermometer and there is a convection here, and because of the convection we use the formula from the Q convection to sensor equal to Q dot radiation from sensor. This one represent the meaning of each one of the symbols. Okay, so the last term in the equation is due to the radiation effect and represents the radiation correction. Okay, move on to the next slide. There is radiation exchange with emitting and absorbing gases. Okay, so the most important parts of these slides is it shows that if a scattered radiation, a non-participating medium that is completely transparent to thermal radiation. Okay, so when the combustion gases in a furnace of a combustion chamber, for example, contain sufficient amounts of H2O and CO2, that is hydrogen and carbon dioxide, and thus the emission and absorption of gases in furnaces must be taken into consideration. Okay, we move to the next slide. There is a shows the three parts. There is a participating medium, gases emit, and the emission and absorption characteristic. Okay, so from this explanation, we can conclude that if the emission and absorption of radiation by hydrogen and carbon dioxide only since they are participating gases most commonly encountered in practice. Alright, we move on to the next slide. That is radiation properties of a participating medium. As we all can see from the figure 13-34, the attenuation of a radiation beam while passing through an absorbing medium of thickness. We use some law here. There is a Beer's law, and it shows that spectral absorption coefficient of the medium. This one is formula, and the spectral transmissivity. This one is a formula from that. And after that, okay, from these slides we can see that it uses the Kirchhoff's law, that is the spectral emissivity of the medium. Okay, after that, okay, this one is the wavelength that includes in the emissivity and absorptivity of gases and gas mixtures. Okay, so the shape and the width of this absorption bands vary with the temperature and pressure, but the magnitude of absorptivity also varies with the thickness of the gas layer. Therefore, absorptivity values without specified thickness and pressure are meaningless. Okay, we will move to the next slide that show the emissivity correction factor. So this one is pressure correction factor, and this one is emissivity correction factors. After that, okay, this one is the graph that shows that when hydrogen and carbon dioxide gases in a mixture of non-participating gases at a total pressure of 1 atmospheric pressure for a mean beam length of L, 1 meter atmospheric equal to 3.28 feet per atmospheric. Okay, this one is another graph, and the last one is the graph for presentation of gas and mixture. Okay, this one is from table 13-4. This is the mean beam length L for various gas volume shapes. Okay, as for summary, we can view and learn that the view factor and the view factor relations, and after that we can learn that radiation heat transfer is from the black surface. That means that it involves the surface involve the color of the shapes. Okay, after that we learn that radiation heat transfer in a diffuse gray surface. So the next one is radiation shields and the radiation effects, and radiation exchange with emitting and absorbing gases. So I think that's all from me. Thank you.
So next, I will present about one of the problems from the fundamental of thermal radiation. So I found this problem from the Chennai heat transfer 5th edition. So what example I took is example 12.2 about the light emitted by the sun and by a light bulb. So before I go to the solution, I will read the question first. So charge coupled device, or we call CCD image sensor, that are common in modern digital camera respond differently to light source with a different spectral distribution. Their line and incandescence light may be approximated as a black body at the effective surface temperature of 5080 Kelvin and 2080 Kelvin, respectively. Determine the fraction of radiation emitted within the visible spectrum wavelength from 0.4 ohm-meter violets to 0.7 ohm-meter reds for each of the lighting source. So I will go to the solution. So this is my solution from the books. So we have one of the data from the question. So if you see that we have a delta 1 0.4 and delta 2 0.76. We got the temperature sun 8080 Kelvin and the black body radiation function delta 1 temperature and delta 2. So we found the delta T and delta 2T to determine. So how we got the delta 1T and delta 2T? So from the delta we times with temperature. So we got delta 1 and delta 2. So for delta 1 temperature we got 2320 ohm Kelvin. So that's we call the fraction delta 1 daylight. So and secondly we found the delta 2 time delta 2 temperature. So 0.76 ohm-meter times 5080 Kelvin. So we got 4488 ohm Kelvin. So there is a F delta to daylight 0.550015. So how we got the fraction of visible fraction radiation? So from the fraction delta 1 and fraction delta 2 we minus. So we got 0.550015 minus 0.124509. We got 0.426. So we will convert to percent. So we get the 42.6%. Before I forget, so this is a table what we get the fraction data. So 0.4 and 0.76. So the fraction data from the 0.4 and 0.6. If you see the shaded region for the data for the fractions. So next we want so what information we get is temperature for the incandescent light bulb. So we got a 2000 Kelvin. So how we want find? So the same step. So we got the data 1 temperature. So 0.4 times 2080 Kelvin. So we got 1120. So we got the fraction data 1. So same with the data 2T, we got the 2128 Kelvin. So we got a 0.0885090. So how we to determine the fraction of radiation of light bulb? So same the step with the fraction of the sign. So we from the fraction data 1 minus to fraction data 2 is the same. So we got a 0.0888590 minus 0.001409. So we got a 0.087, or we call the 87.9%. So this is about the calculation how to determine the radiation from the fraction. So that's all for me. Thank you.
Okay, hi, my name is Nur Syafiqah Izzati binti Afzani Rizal. My matric number is DD1800078. Okay, I will explain about question topic of radiation heat transfer diffuse glass surface of 3D. The radiation heat transfer in a cylindrical furnace. Okay, the question is consider a cylindrical furnace with RO equal to H equal to 1 meter. As shown in figure, the top surface 1 and the base surface 2 of the furnace have emissivities strain 1 equal to 0.8 and strain 2 equal to 0.4 respectively, and are maintained at uniform temperatures. T1 700 and T2 is 500 Kelvin. The side surface closely approximately a black body and is maintained at a temperature of T3 equal to 400 Kelvin. Determine the net rate of radiation heat transfer at each surface during steady operation and explain how the surface can be maintained at a specific temperature. Okay, this is the figure. Okay, from this question, the surface of a cylindrical furnace are maintained at uniform temperature. The net rate of radiation heat transfer at each surface during a steady operation is to be determined. Okay, we can make three assumptions from this question, which is the first one is steady operation condition exists, and the second one is the surface of impact diffuse and gray, and the last one is convection heat transfer is not considered. Okay, we go to the solution. Okay, we will solve this problem symmetrically using the direction method to demonstrate its use. The cylindrical furnace can be considered to be a three-surface enclosure with surface area of area 1 equal to area 2 equal to pi RO squared. RO is 1 meter and we calculate, we get 3.14 meter squared. Okay, for the A3 is the formula is 2 pi R naught times with H equal to 2 pi times with 1 and times with 1, and we get 6.228 meters squared. Okay, the view from the base to the top surface is from figure 13. The F12 is 0.38. Then the view factor from the base to the side surface is determined by applying the summation rule to be F11 plus F12 plus F13 equal to 1. Then you can calculate F13, which is 1 minus with F11 and F12, then we will get 0.62. Okay, since F11 equal to 0, nothing that the top and bottom surface are symmetrically about the side surface. F21 equal to F12 equal to 0.38 and F23 equal to F13 equal to 0.62, and the view factor F31 is determined from the reciprocity relation. Okay, this is the reciprocity relation, which is A1 times with F13, we will get A3 times F31. Okay. We want to find F31, which is F13 multiplied with A1 divided with A3, and we will get the value is 0.31. Also, F32 equal to F31 equal to 0.31 because it is symmetry. Now that's all the view factor are available. We apply equation to each surface to determine the radiosities. Okay, this is the equation for three surface, which is top surface, bottom surface, and side surface. From this formula, we just substitute the value that we calculate above. Okay, then we will get the answer is J1 equal to 11,418, J2 equal 4,562, and J3 is 1,452. Okay, then next is the net rate of radiation heat transfer at the three surface are determined from this formula, which is have Q1, Q2, and Q3. We just substitute the value of A1, F1, to 2, J1, to 1, F1, to 3, J1 minus with J3, then we will get for Q1 is 27.6 kilowatt, Q2 is negative 2.13 kilowatt, and Q3 is negative 25.5 kilowatt. Okay. The algebraic sum of these three equations must be equal to 0, which is we just sum out the value of Q1, Q2, and Q3. We must equal to 0. To note that direction of the net radiation heat transfer is from the top surface to the base and side surface. Okay, this is the summation. Okay, to maintain the surface at the specific temperature, we must apply heat to the top surface continuously at a rate of 27.6 kilowatt while removing 2.13 kilowatt from the base and 25.5 kilowatt from the side surface. The direction method present here is straightforward, and it does not require the evaluation of radiation resistance. Also, it can apply to include with any number of surface in the same manner. Okay, that's all from me. Thank you.